Okay. Uh, in the previous class, we have discussed till selection sort. Fine. That is a portion for your in-assessment examination, which is scheduled next week. Okay. So the syllabus is till chapter 4, excluding insertion sort. Insertion sort is not included. It is still selection sort. So you have binary search, linear search, bubble sort, quick sort, merge sort, and selection sort. Okay. So the complete portion is two modules. Object oriented programming module and design and analysis of algorithms module till chapter 4. Okay, that is a portion for your in semester examination or the midterm examination scheduled next week. All right. To continue with the syllabus, let's discuss one sorting algorithm which is left out in chapter 4, and then let's move on with the next chapter, that is chapter 5. Again in chapter 5 we'll be discussing some more algorithms. Fine. Now we'll discuss about a sorting algorithm called insertion sort. Fine. So you know that there are different techniques, or I can say different what should I say, algorithmic techniques. Fine. You have brute force method, you have greedy technique, you have divide and conquer method, you have decrease and conquer method, you have dynamic programming technique, and so on. Okay, these are all the algorithmic principles or algorithmic techniques that are adopted in the design of some algorithms. Okay. So insertion sort algorithm is one technique of decrease and conquer, or I can say it works on the principle of decrease and conquer. Why the name decrease and conquer is, here insertion happens by decreasing the problem size. Okay, you have one array. Fine, you have an array. Somewhere you apply the method so that the array size is decreased, and you repeat the iteration on the problem of smaller size. Okay, so decrease the size of it, and it is not actually dividing a kind of thing. It is the entire array, some portion of it you take it, you sort it, again some other portion you take it, you sort it, and you do it. Okay, and you finally combine them. Fine. So the algorithm part I will discuss later. First you understand the problem, then let me discuss or let me explain you the algorithm. Okay. So we'll look at the illustration of insertion sort. Your array has 6 elements: 5, 4, 10, 1, 6, 2. This is 0, index 1, index 2, 3, 4, and 5. And the value of n is 6. There are totally 6 elements: 5, 4, 10, 1, 6, 2. Now, basically, when I say it is insertion sort or it is decrease and conquer method, the array should have two parts. Okay, one is unsorted sublist, I can say. Other one is sorted sublist. Fine. So you are considering the unsorted array and the sorted array. Fine. And basically the unsorted array, you take one element from the unsorted array, pick an element from the unsorted array and put it or insert it into the sorted array in the proper order or in its actual position. Fine. That is what happens in case of insertion sort. In every iteration, take one element from the unsorted array and insert it into the sorted list in the actual position of sorted list. Okay, that is the overall technique. Okay, now how to do this? You have 5, 4, 10, 1, 6, 2 as your array. And in the beginning, since we do not know how many elements are sorted, how many elements are not sorted, we will assume that only the first element is in the sorted list. Okay, and remaining n minus elements are unsorted. Okay, initial assumption what we do is we will assume that a of 0 is sorted. Okay, a of 0 is sorted, and a of 1 to a of n minus 1 is unsorted. Okay, that is a first assumption. Now, basically we require two indices, two for loops. Okay, one is I loop, one is j loop. Fine. We require, it is nothing but a kind of pointer or an index. So you require two such indices, one pointing to the sorted list, one pointing to the unsorted list. As I said, in every iteration you are taking one element of the unsorted list and you are inserting it into the sorted list. So if I consider a pointer I pointing to sorted list and an index j, or instead of pointer, let me take the word as index j pointing to the beginning of unsorted list. When you have just one element in the array, you know that it is sorted, right? You just have one element. It is sorted. It is in its actual position. That is why we are making an assumption that the first element is sorted, or it is in the sorted list, and the remaining n minus 1 elements are unsorted. Okay. Now I have two indices, I and j. So what actually happens is, in every iteration, when you pick an element from the unsorted list, you have to see if this element is greater than the element in the unsorted list. If it is greater than unsorted or the first element of the unsorted list, then you can insert directly onto the end of the sorted list. If this element in the unsorted list is less than the element or the first element you consider in the sorted list, then you need to continue the loop in the sorted list till you reach the beginning. Okay, basically this should move in the reverse order, that is you are decrementing it, whereas j index should move in this direction. Okay, this is incrementing. In every iteration you increment the j loop, so that in the first iteration you consider 4, add insert it into the sorted list. In the next iteration you consider 10, add it to the sorted list, and so on. So you are incrementing j. Whereas when you consider say element 4, in the first iteration you compare it with 5. Okay, so I is always j minus 1. In every iteration you should have I starting with j minus 1. So 4 is first compared with 5. If 4 is less than 5, then it should be compared with the element to the left of 5. So in every iteration you are actually decrementing I. Okay, so I is equal to j minus 1 should be set in every iteration for every element you take from the unsorted list. Okay. Now, as I said, your I is pointing to 5, j is pointing to 4. You are supposed to compare. Please understand the method completely. You are comparing a of I with a of j. Before comparing this, let me consider a temporary variable called temp, okay, which holds the value of a of j. So here temp is equal to 4 because a of j is 4. Okay. Now you need to compare a of I with temp. You will understand the reason why I am taking temp. Okay. So basically when you perform swapping, there could be some way of overwriting the array element, and there is a chance that original element is lost. Original value is lost. Okay. So basically in case of insertion sort, you are overwriting some contents or some position or some elements of the array. That is the reason it is always safe that you keep. You must be knowing when you are swapping two elements of the array, you are keeping a temporary variable, right? So this purpose is same here. Fine. Now temp is 4, which is nothing but a of j. Now you are comparing a of I with a of j or temp. So here 5 and 4 are compared. Okay, 5 and 4 are compared. Since 5 is greater than 4, you can see a of I is 5, temp is 4. A of I is greater than 4, right? Since a of I is greater than 4, what you do when a of I is greater than temp, you need to shift A of I one position to the right. What do you mean by shifting one position to the right? You are not actually moving. Original content will be as it is. Plus one position to the right is nothing but A of I plus 1, right? So if this is index 0, this is index 0, one position to the right is A of 1. Okay, so you are shifting A of I one position to the right. So even the second position in place of 4, you will have 5. Okay, remaining as it is. Hope you understand. I will repeat the process again. 5, 4, 10, 1, 6, 2 is your array. 5, I have made a mark here. 5 is sorted and the remaining part of the array is unsorted. You make a comparison of A of I and temp. This is kept in temp. 4 is kept in temp. A of I is 5 because your I index is pointing to this element in the sorted list. J pointer is pointing to first element of unsorted list. You are comparing 5 and 4. Since 5 is greater than 4, definitely you cannot insert this 4 to the end of sorted array because 5 is greater than 4. Then you need to shift. It is actually you need to swap the positions, right? 5 and 4 have to be swapped. But here there is no concept of directly swapping. Instead, you are shifting this 5 here. Okay. When you are shifting this 5, it is actually a duplicate entry. 5 will be there in the original place, plus the copy of it will be kept in A of I plus 1. Okay. So now it is 5, 5, 10, 1, 6, 2. After doing this much, you have to decrement I. Okay, you have to decrement I. I is initially here. J is pointing to this position. When you decrement I, you have nothing here, right? Because you are in the 0th position here. Okay, so you have to run the loop from 0 or till you reach 0. I have to be decremented till you reach 0. And since you have already reached 0, since nothing is left out to the left of it, this A of I should be replaced with the value of temp. So temp is 4. So 4 have to be replaced in the position of A of I. So it will be 4, 5, 10, 1, 6, 2. And now you know that first two elements are sorted. By the end of first pass, you get first two elements sorted. Okay. Now, let me explain you one more step to consider the third element. You will be more clear. You have 4, 5, which is in the sorted list now. 10, 1, 6, 2 is in unsorted list. Okay. Now, I pointer, you have again set, you have to set, this is one iteration for one value of j. Now, you are considering the second value of j. So, j is pointing here. Okay. You are incrementing j. After this one complete pass, you have to increment j plus plus. Okay. When you do j plus plus, j will be pointing to second index 0, 1, 2. Okay. 3, 4, 5. When you do this j plus plus, immediately you have to set the I pointer to j minus 1. So that I will point here and j will point to this. Okay. Now, again you need to keep a temp. You know that temp is always A of j. So A of j is 10 here. Okay. Assuming that this array is A of j is 10. Now, you need to compare A of I with temp. Okay, A of I with temp. And when you compare A of I with temp, A of I is 5, temp is 10. Fine, A of I is 5 and temp is 10. And A of I is less than temp here, right? Because 5 is less than 10. When 5 is less than 10 or when A of I is less than 10, you know that this has to be inserted to the end of this sorted list, right? This just have to come here. Okay, so this should be 10 should be added to the end of the sorted list because after 5 you get 10. So in the sorted list 4, 5, 10. So whenever you come across a condition where A of I is less than 10, then directly you can add or you can shift, or I can say the better word is insert. Insert A of j to the end of the sorted list. Okay. So it is basically A of I plus 1 is equal to 10. Okay. A of I is equal to 10. Fine. So after doing this, it is 4, 5, 10 is in the sorted list. 1, 6, 2 is in the unsorted list. Okay. So when A of I is less than temp, A of I plus 1 will be temp. Okay. Otherwise, A of I will be temp. Fine. Now, second pass is done. Your second pass, 3 elements are sorted. Okay. Now you are moving to the third pass. So again, you need to increment j plus plus, and I is equal to j minus 1. It is inside every outer loop you need to perform this. Okay. Fine. Now, I pointer is here, j pointer is here, j index is here. Okay. So again repeat the process. Your temp is now 1. Okay. Temp is 1. Compare A of I with temp. A of I is 10. Temp is 1. So A of I is less than temp. When A of I is less than temp, what you do? When A of I is less than temp, what you do? Condition is this one, right? Sorry. A of I is greater than temp. Are you listening?
Yes,
Miss Wicked,
ma'am.
you are just keeping quiet now. Here A of I is 10, temp is 1, A of I is greater than temp. You have come across a similar condition here. When A of I is greater than temp, you need to shift A of I one position to the right, that is A of I plus 1. So your array will be 4, 5, 10, which is sorted. This 10 is shifted one position to the right, so it is 10, 6, 2. You can see now when this shifting happens, the original value of A of j is lost. That is the reason we keep it in temp. Okay, copy is kept in temp. So 4, 5, 10, 10, 6, 2. Now I is initially here, j is initially here. After doing this, okay, you have to decrement I. Decrementing I should happen till I reaches 0. Okay, till I reaches the first index, you should decrement the value of I. So decrementing the value of I means I will be pointing here. Okay, I will be pointing there. Now you are again comparing temp, which is nothing but the 1, value is 1, with A of I. So 5 and 1 will be compared. 5 and 1 will be compared. So when you compare 5 and 1, again A of I is greater than temp. I think I will move to the new slide, new thing. Okay, you will understand it better. So you had 4, 5, 10 in the sorted list. 10 is shifted. So 10, 6, 2. Now you have decremented I is pointing here. You have j here. Okay, temp is 1. Now again you are comparing A of I with temp. Okay. So A of I is greater than temp. Again 5 is greater than temp, which is 1. In that case again shift. You have to understand the process completely. Shift A of I to A of I plus 1. So after doing this, can you tell me what is the array content? 4, 5 as it is. Now A of I is here. A of I plus 1 will be here. This have to be replaced with the value of A of I. So it is again 5. Whereas this is 10, 6, 2 as it is. What next? Next is you are decrementing I again. This should happen till you reach the beginning of the sorted array, right? So decrement I, from here I will point to this now. Okay. Now again you need to compare a of I. A of I is nothing but this element with the temp. Temp is the value you have considered from the unsorted list to sort. Okay. So again a of I is 4. 4 is greater than temp because the value of temp is 1. Okay. So when a of I is greater than temp, again you need to shift a of I to a of I plus 1. Okay. When you do this, 4 is as it is, which is a of I. A of I plus 1 is 5, which will be replaced with the value of 4, and the remaining elements are as it is. Okay. Now from here, again when you decrement I, the condition fails because I should be greater than or is equal to 0. Okay. So there is no element further. The condition fails, and when the condition fails, or when you come out of this loop, you have to directly replace a of I with temp. Okay, swap. So when you replace a of I with temp, temp is 1. So this is replaced with 1, 1, 4, 5, 10, 6, 2. You can see that it is not here now. Element is inserted to the sorted list. So the first 4 elements are sorted. Okay. So if you see here, by the end of first pass, 2 elements will be sorted. By the end of second pass, 3 elements will be sorted. By the end of third pass, 4 elements will be sorted. Okay. So when there are n elements, you require n minus 1 passes. Okay, it's basically like that. Now, fourth pass is n is equal to 4. Your I is pointing, sorry, j is pointing here because you have done j plus plus. I will be pointing here because I is equal to j minus 1. Okay. Again, repeat this entire process. Temp is 6. Temp is 6. So 6 have to be compared with a of I. A of I is 10. A of I is 10. 10 is greater than 6. Okay. When 10 is greater than 6, when a of I is greater than 6, you need to shift a of I 1 position to the right. That is a of I plus 1. When you do this, your array will be 1, 4, 5, 10 as it is because this is a of I, which should be copied to the next position, a of I plus 1. Okay. Again, you are supposed to decrement I. After this, you decrement I. Decrement I means I will point here now. Okay. Again, compare a of I with temp. Now, a of I is 5. Temp is 6. A of I is less than temp. When you come across this condition, you have to write a of I plus 1 is equal to temp. A of I is this. A of I plus 1 will be this. Okay. So this have to be replaced with the content of temp. So new array will be 1, 4, 5. In place of 10, it is temp. So temp is 6. I will insert 6. The remaining elements as it is. This is not 6, sorry, this is 2. Okay. Now you can see first 5 elements are sorted. It is simple. Okay. When a of I is greater than temp, you are shifting the element 1 position to the right and you are decrementing I and you continue with the loop. Whenever you get a of I less than temp, you are replacing the next element with the temp and you close it. Okay. Now, you have done this much. Again, you do j plus plus. I is equal to j minus 1 so that j will point to 2. I will point to 10. Okay, repeat the process again. What is your temp now? Temp is 2. Okay, temp is 2. You have a of I is 10. Compare a of I with temp. A of I is of course greater than temp here. 10 is greater than 2. Then you perform shift. Okay, shifting a of I 1 position to the right. So this have to be moved 1 position to the right. your array will be 1, 4, 5, 6, 10 and 10. Okay. Again, you decrement I. Okay, decrement I. After shifting, you need to decrement I till you reach the beginning of the array or you get the correct position in the array. When you decrement I will point to this. A of I will be 6. So 6 is again greater than 2, right? A of I is again greater than 10. When this is the case, again you need to shift A of I. So 6 have to be shifted and the array will be 1, 4, 5, 6 and A of I plus 1 will be now again A of I and this is 10. Okay, again decrement I will come here now. Okay, so A of I will be 5. 5 is again greater than 2 because temp is 2. Repeat the process. Shift A of I. So when you do this, your array will be 1, 4, 5 and this you have to shift one position to the right. So it will be 5 again and this is 6 and this is 10. Again you need to decrement I. Okay. So your decrement I, your I will point to this particular value 4. You are comparing 4 with the 2. 4 is again greater than 2. Again perform the shifting. New array will be 1, 4 and 4 have to be shifted one position to the right. So it is 4 again. Then 5, 6 and 10. Decrement I again. Okay. Now I will point to 1. 1 greater than 2 is false. Instead it is 1 is less than 2. When you have a condition of A of I less than temp, what you do? You are writing A of I plus 1 is equal to temp. And when you do this, your array will be 1, which is A of I. A of I plus 1 should be temp. So value of temp is 2. Okay. Value of I is 2. Then it is the same array 4, 5, 6 and 10 and you can see all the elements are sorted. And this is where you end your loop. So outer loop should run n minus 1 times. Okay. And the inner loop is based on the condition or based on the elements in the sorted list. Okay. If the sorted list has one element, then you can see in the first pass comparison is only once, right? When your sorted list has 2 elements, comparison is maximum number of comparisons is 2. When the elements in the sorted list is 3, maximum number of comparisons is again 1, 2, 3, 3 comparisons and so on. Okay, it is basically the number of elements in the sorted list. Okay, so the outer loop is n minus 1 times, I can say, because the number of passes. Any doubt here? Any doubt here? Have you understood? How many of you understood? Please raise your hand. There are anyway 42 attendees. Let me see how many of you have understood. Please raise your hand. 1, 5, 6, 7, 10. That's all. 12. Okay. Okay. All right. You can lower your hand. If you have understood, I will give you a problem. Please try working out this. Okay. Take down the problem. I will give you a small array. Okay. N is equal to 4. The elements are 16, 12, 67 and 11. Quickly tell me how many passes, how many comparisons, and so on. And if anybody does it properly, I will make you a presenter and you can share your screen, or you can show me, you can turn on the video and show me. Okay, quickly do it. I want at least one solution from your end. Okay, you can turn on the video and show me your book if you wish. Anything is fine for me, but I want at least one solution now. Quickly do it. Whoever solves first will get some reward. Some reward. Quickly do it. I will be making a note of this, and whoever does it properly and shows it to me will get some reward, and you get to know the reward by the end of the semester. Okay? Before your attendance and marks are finalized. Are you doing it? How many of you are trying? At least raise your hand, because you don't respond now. Orally you don't respond. At least raise your hand. How many of you are trying this? Good. Okay. Okay. Try. Good. I want the solution. Let me know once you are done. Finished? Anybody finished? Yes, Harshvardhan. Not Harshvardhan. Who is that? Sorry. Who is that speaking? Anybody finished? Somebody is speaking and it's not clear. What happened? Who finished? Anybody finished? Please show the solution or at least put it in the chat or anything like that. Click a picture and put it in the chat. Are you still doing? At least give some response, guys. You all can speak, right? When you don't answer my question or when you don't respond for my words, definitely you will not be given any chance to ask your doubts during the exam or any other time. Please. Okay, or after the evaluation you should not come for the marks or anything like that because you don't respond in my class, right? Are you doing the solution still or no? Just let me know that. I got one solution. Okay, but when you do the illustration, you are supposed to show the complete illustration. Okay, when you are asked to show the illustration of something, you are supposed to do how I did, comparing or writing every condition and showing the shifting and everything. Okay, if you show us this particular diagram, what you have posted, yes, I don't say it is wrong, but it is not very clear what type of sorting techniques have been applied. Okay, yes, it is sorting, unsorting, you have bifurcated and everything is fine, but show with all the steps, otherwise it will not be considered as a illustration. Okay, fine. I got one solution and that is fine. Now you can look at the algorithm. Okay, since if you have understood the illustration part of it, you will understand the algorithm easily. You can see that there is one while loop, for loop running from 1 to I minus 1. The reason for running it from 1 to I minus 1 is A of 0 is considered to be a sorted list, right? And sorted list index is I, J index is for unsorted list, and your in the first iteration you assume that this is my A of 0 and A of 1 to A of n minus 1 is considered to be a unsorted list. Okay, that is why J index is for unsorted, which runs from 1 to n minus 1, and in every iteration you will be incrementing this J loop. Okay, now inside the J loop, what you do, your initial iteration, you are considering the first element of J as temp, right? So temp is equal to A of J. You are doing, you have observed it in every iteration in the consequent steps. First thing what we do is we initialize the value for temp. Okay. So temp is equal to 2, temp is equal to 6, which is nothing but the value pointed by J pointer. Okay, value pointed by J pointer. So temp is equal to A of J and I is equal to J minus 1, which you have done here, right? I is equal to J minus 1. Every iteration you need to do this. I is equal to J minus 1. For every element picked from the unsorted list, you need to perform this. Okay, I is equal to J minus 1. After doing this, you are running the while loop while I is greater than or is equal to 0. You start from J minus 1, okay, J minus 1 till I is greater than or is equal to 0. That is, you consider J minus 1, you compare with this. Next, you decrement, you compare with this. And then you compare with the last element or the first element of the array, and then you terminate the loop. That is why the condition is I greater than or is equal to 0. And temp is less than or is equal to A of I. Okay. Temp is less than or is equal to A of I. You have a condition here. Temp is less than or is equal to A of I. Okay. So when this is a condition, then what you do, A of I plus 1 is equal to A of I. You are shifting, right? You know that. Yeah. So where you perform the shifting? See here. When A of I or when temp is less than A of I, you need to shift A of I to A of I plus 1. Okay. So when temp is less than or is equal to A of I, you need to shift A of I to A plus I plus 1. Then I is equal to I minus 1. You compare and you loop it. How long you do? As long as the value of temp is less than or is equal to A of I. When temp is greater than or is equal to A of I, then you terminate this while loop by replacing A of I plus 1 is equal to temp. That we have done here, right? When temp is greater than A of I, you terminate the loop by inserting the temp in A of I plus 1 position. That's the same condition. Okay. When A of I is less than temp or when temp is greater than A of I plus 1 will be temp. That is this. And you end the loop. Okay. So it's a straightforward method. You can see we require one loop here, J loop, and one loop here for swapping. Okay. So you have the J loop and you have the I loop inside the while loop. Okay. And you know that your I loop varies from J minus 1 to 0. Right? J minus 1 to 0. So that is how your I loop varies. And the number of comparison you are doing is you are taking an element from the J loop and you are comparing with the elements of the I loop. Okay. So basically inside the I loop, or for I can say in case of the sorted list or I loop, there will be maximum of J minus 1 comparisons. Maximum of J minus 1 comparisons. And you have the J loop running from 0 to n minus 1 again, or I can say 1 to n minus 1. Okay. So since you require two for loops here and the outer for loop is running basically as a constant, it is O of n, right? And the inner for loop is J minus 1 times, okay, J minus 1 times, which is approximately equal to O of n because J loop runs n times, which is approximately equal to O of n times. The worst case time complexity will be O of n square. So the basic operations here are swapping and comparison. The swapping approximately happens O of n times and comparison also happens approximately O of n times. Okay. That is why the worst case time complexity of this insertion sort will be O of n square. Okay. And average case and best case are out of the scope of your syllabus, so we are not bothered about the average case and best case of insertion sort, but you just need to understand how do you get the worst case complexity. Okay, so just for remembering the complexity, you have bubble sort, you have insertion sort, and you have selection sort. I am just pointing out the important ones, and you have quick sort. Okay, of course you have a merge also. Let me just compare these four algorithms, which basically are similar. Okay, the complexity. If you consider the worst, average, and best, it is just for you to remember. Okay, just to recall the complexities, whatever you have done. What is the worst case complexity of bubble sort? If anybody remember, okay, anybody remember bubble sort? Bubble sort, what you do? You pick the largest element from the array, put it to the end. From the remaining elements, again pick the largest element, put it to the end. You remember the outer loop I is equal to 0 to n. Just a minute, I'm getting a call, 1 minute. Yeah, sorry, that was an emergency call. Uh, we were discussing about, or we were comparing the complexities. Just try to recall that in case of bubble sort, you have outer loop for number of passes, which is from 0 to n minus 1, and you have inner loop running from 1 to n minus I minus 1. I do not know how many of you remember. So basically, it is two loops running approximately n times, so O of n square. And just concentrate more on the worst case complexity, because that is where you need to provide the improvements on. Okay, so always when you design your algorithm, the worst case complexity should improve. Okay, best case is anyway the minimum number of iterations. And for the insertion sort, we discussed just now, it is O of n square. And just to remember this, you do not want the derivation of average and best case, but you need to know how do you arrive in this worst case complexity. Now, the selection sort, how do you or what is the method for selection sort? We discussed in the previous class. Can somebody tell me what is the algorithm for selection sort? In every pass, you are finding the minimum element and swapping it with the first element in the first iteration. In the second iteration, find the minimum from the remaining, swapping it with the second element, and so on. Okay, which happens inside again two for loops, right? One for loop running n minus 1 times, second for loop from 1 to n, right? So it is again the same thing, O of n square, O of n square, and the worst case is all, I mean best case is also O of n square. You should please remember, okay, every analysis we have discussed. And the quick sort is something which you need to concentrate on the illustration part of it. It is not very easy. So O of n square we have discussed the worst case. Again, we have not derived average and best. I have just put it as 1 point n log n, and the same thing O of n log n. Okay, for you to remember the analysis of various sorting algorithms. Okay, and basically quicksort is preferred over other sorting algorithms. Fine. Among these four algorithms, quicksort is preferred because of its better average case. Worst case is anyway the same for all the four algorithms. So apart from this worst case, if you consider the average case of these four algorithms, this is better over other algorithms. That is the reason quicksort is preferred among the four other algorithms. Okay, or among the three other algorithms. Fine. So that is about the chapter 4, where you had some commonly used sorting algorithms discussed with their complexities. Fine. Now moving ahead with the next chapter, that is chapter 5 of your syllabus, Intractable Problems. Okay, Intractable Problems. In the real life situation, you might come across certain set of problems whose solutions might take very large amount of time, or the solution might not exist. That is the worst case complexity is always the maximum number of time taken for the execution of that particular algorithm. So the maximum time could be even getting a solution in the last iteration or not getting the solution at all, right? So the problems whose solutions might take the large amount of time, or there might not be any solution. Such problems are considered to be intractable problems. Okay, and it is very important, or it is necessary to study those problems, intractable problems, and analyze the algorithms to see if there is any feasible solution possible. Is there any scope for the improvement of their time complexity? So in order to understand or find the feasible solution, it's very important to identify intractable problems and provide the solution or study them. Okay, and the reason for these the worst or the maximum or the large amount of time or not getting any solution could be the nature of the input or the complexity of the algorithm. Complexity may be in terms of time or in terms of space, anything it could be. Okay, but there could be some reasons like the input provided, maybe if it's too large, your algorithm might not work properly. Okay, so basically dependent on such things. So here in this particular chapter, the purpose is to study about such problems or intractable problems. Okay, so here in this chapter we'll introduce some approaches to solve intractable problems. Fine, because in real life situations there might be some algorithms which are built on these intractable problems. Okay, so in order to handle such problems, or in order to find a solution to such algorithms or problem statements, it's important to understand the methods or the approaches to solve the intractable problems. Now let's find the differences between tractable problems and intractable problems. We know that some problems or some algorithms could be solved in a finite duration of time, right? They are called as tractable problems. Fine, they are called as tractable problems, and basically these tractable problems are polynomial in nature. Okay, they are polynomial in nature. You know, ax square plus bx plus c. What are these things? What is this equation? It's an equation of quadratic equation. Okay, so it's a general example of polynomial equation, right? Ax square plus bx plus c. Fine. So these type of problems, or finding a root of quadratic equation, you can actually solve it by polynomial time or finite amount of time. We call them as polynomial time algorithms, finding the root of a quadratic equation. Okay. So the tractable problems or the solutions to these problems are polynomial in nature. Okay. Uh, Next, coming to the intractable problem, you know, right? It cannot be solved in a finite duration of time. It requires a larger time of execution to get the solution. Okay. So some algorithms which have the time complexity of n to the power n, it's too large, right? when the input size is vast, the time complexity is the worst to the worst, right? When the value of n is small, it's fine, but as the size of the input increases, the time complexity is unimaginable. Okay, similarly, big O of 2 to the power n. Okay, big O is for worst case complexity, 2 to the power n again. Okay, 5, 10, 15 is fine, 1000, 2000, 10,000 values, 10,000 inputs. Okay, so when the value of n is too high, they cannot be solved in finite amount of time. Okay, you require a huge time or huge amount of time and space to solve them with a larger value of n. That is why such problems with the time complexity, which require the worst case complexity of n to the power n or 2 to the power n, are considered to be intractable problems. So basically this is polynomial in nature, and this is basically they are exponential in nature. Okay, these are called as polynomial algorithms. Okay, the algorithms that are used to solve the tractable problems are called as polynomial algorithms, whereas the problems solved or the solutions for these intractable problems, the algorithms you design to solve these intractable problems are considered to be exponential algorithms. They grow exponentially, right? They grow exponentially. Fine. So then what are these polynomial problems and exponential problems? Okay, I am just giving the definition today. Maybe the problems we'll be discussing in the next class. Okay, so if you have a set of problems, okay, the problems could be intractable and problems could be tractable. Okay, and of course both of them are maybe the solvable ones. Okay, both of them are solvable. Fine, this is a set of intractable and this is a set of tractable. Fine, this is all solutions. Fine, this is just a relationship between tractable and intractable solution. There might be solutions for intractable, but for a designer, for a designing person who is designing the algorithm or the solution, it's very important to distinguish given a problem, what type of problem is it? Is it a tractable solution? Is it an intractable solution? What solution you get? Okay, so it is always important to differentiate the tractable and intractable problems. And tractables are of course the polynomial problems, and intractable are exponential problems. So how do you identify the polynomial problems or P-class problems or tractable problems? When you design an algorithm, and if the algorithms have the polynomial upper bound as O of 1, O of log n, O of n, O of n log n, O of n square, these are considered to be polynomial problems. Okay, these are considered to be polynomial problems. They grow polynomially, I can say, right? Because even though you provide a larger value of n, it will not give you a huge difference in the complexity. Okay, it is not mainly depending, because see, when the value of n is 2, the time complexity is small, but when the value of n is 10, the time complexity is too vast, the difference will be more. Okay, time required is more. So it is, in case of polynomial problems, it is not the case actually. Okay, so they do not vary much. Fine, they do not vary much. So when you get the worst time complexity of 1 log n log n square, etc., these are considered to be the polynomial problems or P-class problems. Okay, and generally, how do you get these worst case complexities is based on the problem statement. Okay, for quadratic type of problems, you get O of n square. For nearly linear, it's O of n log n, linear O of n, O of log n, O of n, etc. for different varieties of or kinds of algorithms. Fine. Then what are the features of P-class problems? Okay, P-class problems are generally decision type problems in nature. Okay, what do you mean by a decision type problem? It is the problem which has the answer as yes or no. You know it, right? If A is greater than 0, yes or no. Okay, answer is just yes or no. Such problems are considered to be decision type problems, and P-class problems are basically decision type problems in nature. And P-class problems are, of course, tractable. Okay, they can be solved by a polynomial time algorithm. Okay, that is why we call them as tractable. And P-class problems are solved by deterministic algorithms. Okay, deterministic and non-deterministic algorithm you will learn later in this chapter. Okay, but as of just as of now, understand that P-class problems are deterministic, whereas intractable problems are non-deterministic. P-class problems are deterministic and intractable are non-deterministic, or it is also called as NP problems. Okay, so I will stop the class here. We'll discuss in the next class. Any doubts? All right. Thank you. There will not be any quiz today. Okay, there will not be